Okay, so what I want to do today is I want to talk about optimization problems. And so, the tripod is probably better. And so I want to talk about optimization problems. So I'm going to review how we did optimization in Calc 1. And essentially the same ideas that worked in Calc 1 work in Calc 3. The only thing that changes is the number of variables you need to look at. So the real start for optimization is to identify what is our goal. And our goal is typically to find out when something is maximized or when something is minimized. So we search for max and min. Right. Anybody tell me from calculus, how do you find a maximum or minimum? Or at least how do you find candidates?
When the derivative is 0.
Okay, everybody agree. All right, I will see if this works. All right, so tell me when you think my speed is greatest. Okay, are we ready? Got to wake them up over there. Yes, what did we do wrong? At the endpoint as well. All right, so I hope for the rest of your life you will never forget to check the endpoints. Okay? It is the most forgotten thing. Right. Okay, so we find critical points. And these are places x such that f prime of x equals 0. And we check endpoints. Now what's nice about this is in one dimension, how many endpoints do you really have?
2.
2. Or maybe 1 if you go off to infinity, or maybe 0. So here, in one dimension, typically it's at most 2 endpoints. Is it unreasonable to look at 2 points and check what's going on? No. 2 points is not bad. The problem is when we generalize to several variables, we're now going to have to worry about having a boundary. And how do you check what's going on the entire boundary? So let's first talk about why the places where f prime is equal to 0, why these are points that are candidates. All right? So these are all candidates. Why are these candidates? Well, let's look at f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. So there are 3 possibilities. This is positive, it's 0, or it's negative. So let's look at see what happens. If it's positive, then for h sufficiently small, if the first derivative is positive at x, what must be true for h sufficiently small? So imagine this whole expression is positive, your f prime is positive at x. I take h to be a small positive number. What must be true about the numerator?
It's positive.
It has to be positive if h is sufficiently small. Otherwise, this limit couldn't be positive. So if positive, then for h sufficiently small, f of x plus h is greater than f of x. Could we be at a maximum at x? No. Just let h be a small positive number and you increase. So thus, x is not a max. And x is not a min. If you just go a little bit before, it would have to be smaller. So because the first derivative is positive, you often have plots like this. Here's f prime, and here's maybe my plot of f. So if f prime at this point is positive, then my function has to be increasing in a small neighborhood. So if my function is increasing to the right and decreasing to the left, this cannot be a maximum or minimum. What would happen if f prime was negative? Well, essentially the same argument. Now you'd be decreasing if you go a little bit past x, and increasing if you go a little bit before x. So what this tells us is the only possible candidate, so only candidates left are x such that f prime of x equals 0 or the endpoints. Because again, the analysis here was saying, let x be a small positive number, go a little bit past. Well, if you're at the endpoint, you can't go a little bit past. That's why we have to check the endpoints separately. Okay? So when we look at this, these give us the candidates. And it's extremely important to keep using the word candidate. Candidate does not mean it attains its max, it attains its minimum. One of the best functions to look at is f of x is x cubed. F prime of x is 3x squared. So what's the critical point? So what would be the critical point here? Yes.
X equals 0.
X equals 0. So is that a maximum or a minimum? Neither. So if you actually plot the function, the cubic is going to look something like this. And if you look at the derivative is positive everywhere except at 0. So it's not enough to find places where the first derivative is 0. They give you the candidates. Then you have to prune the list somehow. One of the best ways to prune the list is take all your candidates, evaluate your functions at these points, and see where it's largest. So here, as I go off to plus or minus infinity, I can clearly see that's going to be my maximum, that's going to be my minimum. So if it's any finite interval, whatever the endpoints are, that's going to be the maximum and minimum. How many of you remember the first derivative test? So plotting skills is something that is typically no longer covered. I will give you a problem later in the semester where it is doable using all of our techniques in Calc 1. It has applications to how computers are built. And it really involves knowing how to graph functions. Now, this is the 21st century. If you have to graph a complicated function, what should you do? Put in your computer, right? I am not going to extol the virtues of pen and paper, plotting. When I was young, we were forced to do this. We were also forced to learn how to use log tables and trig tables. Times have changed. Okay? But it's nice to be able to look at a function and get some sense of what's going on. So sometimes you do the following. Here's my plot of f. Here's f prime. And say, here's my critical point, x naught. And let's say the derivative is 0 here. And let's say the derivative is positive to the right and negative to the left. Well, if the first derivative is positive, my function's increasing. If the first derivative is negative, my function is decreasing. So this tells me it's going to look something like coming down and then going up. I don't know exactly what it's going to look like, but it has to look something like this. So if my first derivative goes negative 0 positive, do I have a max or a min? I have a min. And if I went positive 0 negative, I'd have a max. If I go positive 0 positive, then I'm not going to have a maximum or minimum. And that's going to be the example of the function f of x is x cubed. So you often get the second derivative test as well. So let's say that was the first derivative test. Let's look at x naught as a critical point, and let's look at the second derivative at x naught. Let's say the second derivative is positive at x naught. And we know the first derivative is 0 at x naught. So really, you get to choose, do you want to do the first derivative test or the second derivative test? If you can easily tell the sign of the first derivative, do the first derivative test. Or if you can easily calculate the second derivative, do the second derivative test. If the second derivative is 0, you don't have enough information, and you have to create the third or the fourth derivative test. And if you look at a nice function x cubed, the first derivative is 3x squared, the second derivative is 6x, which is also 0. So you can't use the second derivative test here. So let's assume that the second derivative is positive at x naught. What must be true if we are a little bit above x naught? What would be true of the second derivative? So the second derivative is positive at x naught. What do you think would be true just a little bit past x naught? What would the sign of the second derivative be there? So if you want an actual number, let's say it equals 18 here. What kind of number do you think would be just a little bit past x naught?
Less than 18.
Less than 18?
Are we doing it based off the one you gave earlier? Or just...
Well, I'm just saying right now, all I tell you is the first derivative is 0 at x naught. The second derivative is positive. Let's say it's 18. About how large do you think the second derivative is a little bit to the right of x naught? Approximately how big? Do you think it's negative 20 billion? Do you think it's positive 20 billion? Approximately, what do you think the second derivative is just a little bit past x naught?
18.
About 18. And what do you think it is just a little bit before x naught? 18. This is only true if the second derivative is continuous. If the second, we were talking about transporters earlier today. If you had a transporter, you could instantaneously move to another part. Okay. But if my function is continuous, if it's 18 at x naught, it's going to be around 18 to the left and the right. In particular, if it's positive here, it'll be positive a little bit to the left and a little bit to the right. So if the second derivative is continuous and it's positive at x naught, it's positive both before and above. All right. Now let's take our knowledge of the second derivative and propagate it up to the first derivative. We are reducing things to something we've already known. The second derivative test we're going to prove by looking at the first derivative test. If the second derivative is positive here, what does that mean about the function f prime? So if my derivative is positive, what does that tell me about its function? It's increasing. So if f double prime is positive, which function is increasing? F prime. The second derivative is the derivative of f prime. So since the second derivative is positive here, this means f prime is increasing. Okay, if it's increasing from 0, what value must it take on?
1.
I'm sorry?
A
A positive number. So it must be positive to the right. And if it's increasing and it's 0 here, what must it be a little bit to the left? It must be negative if it's increasing to 0. So by knowing that the second derivative is positive and by knowing continuity, we now know that the first derivative locally looks like this near the critical point. Ah, now this is the first derivative test. And so now I draw the same thing. And so we get as the second derivative test that if you have a continuous differentiable, twice differentiable function, second derivative test. If f double prime is continuous, f prime of x naught equals 0, f double prime of x naught is greater than 0, then max. If f double prime of x naught is less than 0, I'm sorry, it's a minimum, sorry. And if it's less than 0, then it's a max. Right? You should all have seen the second derivative test before. The big thing you have to remember is, if the second derivative is positive, is it a maximum or a minimum? There's an easy way to remember this. And I will try to do this multiple times throughout the semester. How often in life, I feel like a used car salesman or something, or some kind of salesman on like a home shopping network. Is there something that you kind of remember? You remember most of it, but you don't remember all the details. But you have the broad outlines, and you just can't remember some of the small little additional facts. As long as you can remember most of the second derivative test, you can actually get the rest of it. So let's consider g of x is x squared, and h of x is negative x squared. So if I plot this function, that's g of x, that's h of x. G prime of x is 2x, g double prime of x is 2, h prime of x is negative 2x, h double prime of x is negative 2. So if I remember the second derivative test, and I'm trying to remember, does positive mean minimum, does positive mean maximum? Well, let's test it on a function I know. I can plot x squared. I can plot negative x squared. And now if I look at this plot, I see, okay, it's a minimum, and the second derivative is positive. Okay, it must be that positive goes with minimum and negative goes with maximum. So this is a really good way, if you remember most of something, to get the rest. If you have a formula that's approximately correct, but I can't remember where does the sign go, where does the factor of 2 go, this or that, if there's a specific case you can check that case. And then once you've checked that case, then you know what's going on. Okay, so this is optimization in one dimension. Any questions on what we've done here? Okay, so now the question is, how do things change when we go to several variables? And in one dimension, it wasn't too bad. We basically have critical points and we have endpoints. But in several variables, we now have many possible endpoints. In fact, typically we'll have infinitely many of them. And so you need a way to check. One thing you could potentially try to do, at least in 2 dimensions, is write the boundary as a nice curve. And if you have the boundary as a curve, you now have a function of one variable describing where you are on the boundary, and reduce that to a one-dimensional problem. But while you can do that, as you get to higher and higher dimensions, it's going to eventually break down. Or you're going to have to do so many small extra special cases, it's just not going to be worth doing. We will eventually get to a really good technique to allow us to handle things on the boundary. Right now, we're going to concentrate on the interior. So how do you find candidates in the interior? So imagine we have some closed curve like this, and we want to find where the function is maximized or minimized inside. So we're going to search for candidates. And imagine this point here is one of our candidates. So what must be true? So we have some function f of xy. We'll assume it's differentiable. What do you think must be true for this point to be an interior maxima? Or an interior minima? Or at least to be a candidate? Yes?
The derivative of that point is 0.
Good. And so when you say the derivative, that means both partials. So let's just think about this as a one-dimensional problem. If this is a maximum, then that means no matter how I move locally around it, no point goes to a higher height under f. If it's a minimum, no matter how I move, no point goes to a lower height. Well, let's just move parallel to the x-axis. And now we have a function of one variable. If this is a maximum, or if this is a minimum, the first derivative must be 0. And so that tells us we need df dx equals 0. And then if we move this way, we need df dy to be 0. So it follows immediately from the results we did in one dimension. The more challenging thing would be, how do we determine if it's a maximum or minimum? What would the second derivative test be? We have a lot of second derivatives now. So what are the possible second derivatives? So there are 3 or 4 depending on how you look at it. Can somebody give me one second derivative? Yes.
The partial second the derivative of the function.
Okay, with respect to what? So I've got the partial with respect to x, and now what do I differentiate this with respect to? X. So that's one of them. Then we would also have f of xy. We'd have f of yx, which hopefully is the same, and f of yy. And so now there's 4 partial derivatives. And there is a way to combine these and get a second derivative test. Depending on interest and how much time is left at the end of the day, I might talk about this. This is one of the few times in the semester when the answer to what class would be useful is not real analysis, it's actually linear algebra. And if we had linear algebra, there'd be a much better way of understanding what's going on. The second derivative test is going to involve fxx, fyy minus fxy squared. And there's a reason why this is a natural thing to look at. But right now, I don't want to say too much about this. Right now, I'm more interested in finding candidates. And so if we want to have a maximum or minimum, we need to find a place where the partials vanish. We will do an application of this, one of the most important applications in the world. We will do linear regression or the method of least squares. It is incredible how many problems this can solve, where you have some observed data and you're trying to figure out what's the best fit to it. So I have recently done a $3.5 million application of this for the local region that I will talk about. So it is amazing what you can do once you've learned how to optimize functions of 2 variables or several variables. All right. What I want to do now is I want to start doing some actual optimization problems. I'm going to start with some problems that look multidimensional, but we'll be able to convert them to one-dimensional problems. And then we'll get to something eventually that really looks 2-dimensional. Okay, so the comment to do Farmer Brown came in too late, and I forgot to look in my attic to find the book. How many of you know the book Click, Clack, Moo? Cows That Type? It begins, Farmer Brown has a problem. All right. So the way the problem works is Farmer Brown is obsessed with rectangles. No shape will do for his pens for his cows other than a rectangle. And he has, say, 40 meters of fence. What rectangle has the maximum area? He will not consider any other pens other than rectangles. What do you think the answer would be for this problem?
A square.
Probably a square. So let's write down what goes on. So the given is x plus y equals 20. You always draw a picture. Here's x, here's y. Because if the whole perimeter is 40, then half the perimeter is 20. So we're given that, and we want to maximize x times y. So this looks like a problem in 2 variables. And later we'll see how to use this, how to use methods of 2 variables to solve this. It's called a constrained maximization problem. Why constrained? Well, because we have a constraint. X plus y must equal 20. But we can reduce this to a one-dimensional problem. So if x plus y equals 20, this implies that y is just 20 minus x. So we get an area function that's just x times 20 minus x. And what is the range for x? Because we do not want to forget endpoints. Yes?
Greater than or equal to 0, less than or equal to 20.
So that's my range for x. And what's nice is you can clearly see that the area at 0 and 20 is going to be 0. The maximization is not going to happen at an endpoint. All right? We need to find the critical points. How do we find the critical points? Yes? Right. And how do you take the derivative of this?
Well, it would probably be easier to see if you distribute.
Yes. So I sometimes call Henry David Thoreau the patron saint of mathematics. Anybody read Walden? So Thoreau's big advice is to simplify. Now, of course, you could simplify to simplify, but then you lose some of the power. Before you do any math, before you do any detailed calculations, spend a moment, look at the problem and see, can I simplify it and make the algebra nicer? What rule would I have to use to do the differentiation right now? As written. Product rule. But if I simplify, this is 20x minus x squared. Now I'm using the difference rule. I'd much rather use the difference rule than the product rule. So, throw, simplify. All right, so we get a prime of x is going to be 20 minus 2x. So the critical point is 20 minus 2x equals 0. So x equals 10, which then implies y equals 10. And as expected, we get a square. Okay. Any questions about this? So we were able to avoid doing this as a multivariable problem by substituting for one variable and then getting a new one and then writing down what the endpoints would be. In general, you cannot do this, but it's worth being aware of these tricks. Right. I can't remember, in the video, did we do the Farmer Bob problem?
Yeah.
Okay. So let me quickly do Farmer Bob. I'll just, since it was in the video, some of this is too high, so let me try to lower it. All right. So I will quickly just do, so the Farmer Bob is now you have water over here, so you get one side for free. And Bob is trying to figure out how to maximize. You can do the exact same analysis as before. So who is the superhero who helps in the video? Yes? Aquaman. Right? And I think Aquaman is now in the new Justice movies. If you imagine at the same time you have Aquaman down below, and Aquaman is optimizing their rectangular pen, at the same time Farmer Bob is optimizing his rectangular pen up here, it's whatever is the optimal shape up top for the cows is the optimal shape down below for the fish. And so it's really the same as finding what's the optimal rectangle when you have twice the perimeter. And so you'll get that this whole thing would be a rectangle, and now instead of having 40 meters of fence, we'd have 80 meters of fence, so it'd be 20 by 20, so it becomes 10 by 20. So again, sometimes you can use symmetry to avoid problems. All right. I don't believe we did the triangle problem in the video. Is that correct? Okay, and this is why I was playing They Might Be Giants Particle Man, because one of the characters is Triangle Man. So imagine, let's see, who should we be? We now have Barbara. What shape do you think Barbara likes? Triangles, given the fact that I'm talking about triangles. Farmer Barbara will not consider any shape other than a triangle. What shape do you think maximizes the area for triangle? Or what kind of triangle do you think?
Right triangle.
So one candidate is a right triangle. Other candidates? Equilateral triangle. Now, if you were going to do a right triangle, is there any special type of right triangle you'd like to do, or just any right triangle? So there's infinitely many right triangles that have the same perimeter.
So maybe a right triangle where the other two angles are both 45.
Yeah, so maybe isosceles, right? So these two sides are the same. So these are two natural candidates. Some type of right triangle. If I had to choose a right triangle, I'd probably choose a right triangle. I'm sorry, I'd probably choose a right triangle. Or maybe an equilateral triangle. And the question is, which one is best? This is now getting very close to real-world problems. In general, what you'd like to say is, I don't care if it's a rectangle or a circle or a triangle. If I have a given amount of perimeter, what's the maximum area I can enclose? what do you think the answer would be? Maximum area for a given perimeter.
Circle.
It would be a circle. So the circle is the maximum area for a given perimeter. So I actually proved this in one of my fall classes this year. The proof that I like best uses Fourier series, which is a nice generalization of Taylor series, which we'll get to later in the semester. And you can prove that if you have a continuous curve, the best area you can get is if you make it into a circle. What if you had a given amount of surface area? What object do you think might have the greatest volume?
Sphere.
Probably a sphere. So if we're building things, should we build circular buildings? Or should we build spherical buildings? I've seen a small number of spherical buildings, maybe Epcot, but for the most part, we don't have spherical buildings. Why don't we have spherical buildings?
They're just like structurally really hard to construct that way.
So one thing is structurally they are hard to construct. There's another reason. We don't have that many cylindrical buildings. You are all engineers being inefficient? These are buildings made for people. If the cylinder isn't that large, you're going to have big arcs in your building, and that may not be ideal. Because this is being recorded, I will not say where this happened, but there was a business school where they were building a new home for them, and they had a cylinder built. And some of us believed that this was so that there would be no corner offices that professors would fight over, which have 2 windows. And by having a cylinder, you can actually minimize the fights of all these high-powered people moving into a new building. But you also want to think about what it's being used for. How many of you have been to Dulles Airport in DC? So the architect of Dulles built my dormitory in college. There are no right angles in our building. Now there are a lot of 89 and 91 degree angles, but there's also a lot of 60 degree angles. Most dorm furniture is not designed for 60 degree corners. And so while it may be aesthetically very nice, for those of us actually living in the building, it was less than ideal. So you want to think about what you're trying to solve. So the circle might be a more efficient shape, but there could be really good reasons why we would actually want a rectangular building rather than a cylindrical building, even though we could get more area or more volume. It's also sometimes a function of where that volume is, where that area is. So we want to try to figure out what is the optimal triangle for a given perimeter. So we have x plus y plus z equals the perimeter. Does anybody remember the formula for a triangle with sides x, y, and z? There is a formula for the area of a triangle in terms of x, y, and z. If you think about it, if I tell you the sides, does that uniquely determine the triangle? Or at least if it doesn't uniquely determine the triangle, does it determine the triangle's area? So, anybody remember Heron's formula? Sometimes they put an N with the name. Does this sound familiar to anybody?
Yeah.
So S is the semi-perimeter. It's x plus y plus z over 2. And then the area, as a function of x, y, and z, is the square root of s minus x, s minus y, s minus z. So this is Heron's formula. It gives us an explicit formula for the area in terms of the 3 sides. How can I check and see if this is right? Maybe I forgot a 2 somewhere. Maybe I should be using the perimeter, not the semi-perimeter. Do you know any triangles where you know the 3 sides and you can calculate the area easily? Yes?
Right triangle.
Which right triangle?
3, 4, 5.
So 3, 4, 5. So we do a 3, 4, 5 triangle, the area is going to be 6. So for this, the semi-perimeter would be 5, 8, 12 would be 6, and I would get the square root of 6, 6 minus 1, 6 minus 3 is 3, 6 minus 4 is 2, 6 minus 5 is 1, the square root of 6 times 3 times 3 times 1 is 6. So this at least checks, and it doesn't prove that Hero's formula is correct, but at least it gives us some evidence, some reason to believe we wrote it down properly. And again, whenever you can, if you can check formulas and see if you've made a mistake, try to do a simple case. So this gives us some confidence. Right. There's a lot of things I like about this problem. So we are trying to find the choices of x, y, and z that maximize the area. Do you want to maximize the area? Or is there a related function you'd rather maximize? Can you think of a function very closely related to the area that would be better to maximize? Yes?
The area squared.
The area squared. If I maximize the square of the area, that's the same as maximizing the area. Often you will get problems where you want to find the point that's closest to a line or closest to a curve. Instead of looking at distance, look at distance squared. Get rid of the square root. And in fact, we can do something even better. I'm going to look at f of x, y, z is just s minus x, s minus y, s minus z. Why am I dropping the s? It's one thing to square it. We all said that that's fine. But now I'm dropping the s. Why can I drop the s? So I'm trying to find the triangle with largest area given that x plus y plus z equals p. Is x plus y plus z over 2 changing? What is this? What does the semi-perimeter always equal? If I tell you x plus y plus z is the perimeter P, what is x plus y plus z over 2 going to be? P over 2. It's just going to be P halves. If I fix the perimeter, I've also fixed the semi-perimeter. The semi-perimeter is not changing. It's just along for the ride. So do I really need to keep and propagate that s down? No, it's not changing. So if I find where this function is maximized, that will also give me where this function is maximized. And so now I want to replace s with p over 2. All right. Do you want to choose a specific value of p just to make things nice? What do you think a really nice value of p would be?
2.
2. Excellent. Right? So you want to get a sense of scale for problem. So let's look at a triangle. If I rescale, if I double the perimeter, that should just double x, y, and z. Is it going to change the shape of the triangle? No. If I triple p, I just triple x, y, and z. The area changes by a factor of 9. If I triple, fine. I don't care. It's not going to change the shape. So if I want, I can assume that p is 1. I can choose the units I work in. I don't have to work in meters or centimeters. I can work in furlongs. There's a lot of crazy units out there. Later in the semester, we might meet the unit of smoot, which is actually the size of a freshman pledge to the one of the MIT fraternities back in the 1960s. And they measured a bridge in terms of how many smoots it was. Do you think that the smoot is a good unit of measurement? No, this is one of the things you can do as a fraternity when you have pledges. MIT also gave us the Bruno. It's the indentation in cubic centimeters made by a piano of a certain type being dropped from a 3rd floor onto a concrete sidewalk. Okay. Again, you can make up whatever units you want. Sometimes it's helpful to choose good units for problems. Physicists sometimes use the rationalized MKS units, where they change things so that the speed of light is 1 and the gravitational constant is 1, so that these things don't clutter up the equations and you can see symmetries a little bit more. so that the electric and magnetic fields behave similarly. Over here, for a problem like this, I could keep S, I could write S as P over 2, or if I want, let me just choose my units so that the sum of my perimeter equals 1. And so now I'm trying to optimize the function f of x, y, z equals 1 minus x, 1 minus y, 1 minus z. And now, what do you think the ranges are for x, y, and z? What do you think the smallest x, y, and z could be? 0. We're making a triangle. I'm not going to have a triangle with a negative side. What's the largest x, y, or z could be?
1.
1. If x, y, or z was greater than 1, we'd have a negative number here, which should frighten you. But also for a triangle, any side is less than equal to the sum of the other two sides. The only way they're equal is if you actually have a degenerate triangle, which is just a straight line. Because these two lines are coming up. So since the semi-perimeter is equal to 1, the perimeter is equal to 2, no side can be larger than 1. So I now have a function of 3 variables. Here are my boundary points, x, y, or z equals 0, x, y, z equals 1. Do you think that the best triangle is going to happen when x, y, or z is 0 or 1? No, those are all going to be degenerate triangles. This is fortunately the case in a lot of applications. You can argue that the boundary cases, the endpoint cases, don't really matter, and the optimization is going to come in the interior. So now we want to find the place where all the derivatives vanish. What would, when you look at how this depends on x, y, and z, what word comes to mind to describe this dependence? How does it look relative to x, y, and z? So I would say it looks very symmetric. Can you tell the difference between x, y, and z? No. So because I can't tell the difference between x, y, and z, which do you think it is? The right triangle or the equilateral?
Equilateral.
Probably the equilateral, because I can't tell the difference between the three of them, so I would guess that the optimal point would probably be where all three of them are the same. Okay, so now let's quickly try to finish this. So we need to take the partials. The partial of f with respect to x. What would that be? So I just use essentially the constant rule. I've got 1 minus x, 1 minus y, 1 minus z. If I'm taking the partial with respect to x, 1 minus y, 1 minus z is constant. So what's the derivative of 1 minus x with respect to 1? Oh, sorry, with respect to x? Negative 1. So I get negative 1 minus y, 1 minus z. And I get df dy is equal to negative 1 minus x, 1 minus z. Df dz is negative 1 minus x, 1 minus y. Now this is looking interesting. What must be true for these to be 0? So we want them to equal 0. what's the only way that could happen? Yes?
Negative.
I'm sorry?
If like x, y, or z is less than 0, or no greater than 1.
Yes?
At least two of them would have to be 1.
At least two of them would have to be 1. So need at least 2 to be 1. Because this equation tells us either y or z is 0. Let's say y is 0. Then this one would also be 0. And then I would need x to be 0 here. Or if z was 0 over there, then I'd be fine over there. So we need at least 2 out of the 3 to be 0. So we said the semi-perimeter, we said the perimeter was equal to 2, so the semi-perimeter is 1. So if 2 of them are 1, what does the third one have to be? 0. Where's the mistake? Where did we go wrong? Everything seemed reasonable as I was going through it on the board. Right, we start off with Heron's formula. Right? This is the formula for the area of a triangle. We're assuming that the semi-perimeter is fixed, that x plus y plus z is always equal to 2 in this case. Any thoughts as to where the mistake is? So we have the formula for the area. Is it okay to go from area to area squared? That sounds fine. Is it okay to replace the s with the 1? That seems to be the only spot where, because once we do that, here's our function. It looks symmetric. Now, one of the problems, of course, is we have 0 less than equal to x, y, z less than equal to 1. But could they all be equal to 1? Or could even 2 of them be equal to 1? We still have the constraint x plus y plus z equals 2. So when we pass on over here, we're doing something slightly wrong. And I wanted to go through this to show you how easy it is to be doing something that seems reasonable. I thought that that would be a fine set of boundary conditions to write. But this would tell me that I'm looking at a big box in three-dimensional space. Right? X, Y, and Z all go between 0 and 1. I'm looking at the entire box. I'm not looking at a box. I'm looking at x plus y plus z equals 2. What kind of shape is that? So what kind of shape is x plus y plus z equals 2? We've covered this. You've got 3 variables, but you have 1 constraint, so it's going to be a 2-dimensional object. What 2-dimensional object do you think this is? It's a plane. Once you specify x and y, then z is determined. This is a plane. We're really only supposed to be looking at a plane. We're looking here at a box. And so when I convert to this and say that this is my region, I've made a mistake. So I have to be extremely careful with something like this. So what I could do is I can go back in here And I can keep s as equal to x plus y plus z over 2 and go through the analysis like that. And that will be a lot more involved. So I'll leave that for you as an extra credit to just go through and finish this problem and do it correctly. But I really want to emphasize how easy it is to write down the wrong constraints. This is why, how many of you remember integration by parts? I always like to write down explicitly, u equals this, dv equals this, to really remember what's going on. Okay, this is a good place to start. I'm sorry, to stop.